title is Coupling Machine Learning Approaches and Rare Event Algorithm to Compute Extreme Events in Climate Dynamics. So I hope you see my slides now. Yeah. So I will speak mainly about rare event algorithm, actually during the 45 first minutes, to compute extreme heat waves or to compute abrupt change of climate in turbulent flow. And so then I will have 15 minutes more to explain what we began with machine learning and how we want to couple machine learning algorithm with rare event algorithm. So this is the outline of my talk. So I will begin by explaining why rare events can be very important. So in climate, this is obvious for many of you because we all know that extreme events, for instance, extreme heat waves or extreme storm or extreme floods or extreme drought, so they are very important. They are basically what matter the most when we are thinking of climate change. And so those are rare events with a huge impact. So that's why they matter. And so we need to study them specifically. So there are other kinds of rare events that matters. They are abrupt climate changes. So far, we don't know exactly whether our climate may change to a very different climate in the future. So this happened in the past. So we don't know if this might happen in the future. So here too, we are talking of rare events. So we need to study them. So I will make an introduction presenting two examples, and then explaining you how we try to compute these rare events using climate models, but we need to specifically describe algorithm for this. So the main application today will be the probability and the dynamics of extreme heat waves using climate models. But I will also briefly speak of rare transition in atmosphere jet dynamics. And then I have another set of slides with which I will talk about machine learning. Do you see my my mouse when it moves on the screen?
Yes.
Okay, thank you. So please ask me a lot of questions. This will be very, very helpful. I begin by this map of Western Europe during 2003. Maybe you have heard about the 2003 heat waves over Western Europe. So it was a huge heat wave, the largest we have seen in mid-latitude probably. So it killed something like 50 to 70,000 people on top of a usual number. So it was not as much as COVID, but it's the same order of magnitude. And so it happens. You see on the map the temperature anomaly. So you see that the red color is 10 degrees. So 10 degrees does not seem much. 10 degrees, it's the typical fluctuation of the temperature we have. But actually, this is an average over a month. So having a fluctuation of 10 degrees on average during a month means that many times it was much larger than 10 degrees. And it had a huge impact over the population. So on the right, you see a picture in Paris where it is written that if you have lost one relative and you don't know how to find it, there is an emergency number you can call. So this is just to illustrate that in France and in many other countries, the state was completely overwhelmed by these events. So as a scientist, the question is, what is the probability of these events? What is its return time? So when will we see an event like that next time? So this is the return time. And so it's a very important question. So the basic answer by scientists is we don't know. We don't know neither for the past climate nor for the future climate. If you look at the literature, the scientific literature, you can find for return time for these events any numbers between a few centuries and 10,000 years, basically, with talking about pre-industrial climate. So why don't we know? Well, we don't know because we don't have data. This event has never seen before. So we have never seen anything like that before. So we cannot rely on data. So we have to rely on model. There is no other choice. And the point is that the model have problems. They are very good. It's amazing what the climate model can do, but there are some bias, and we don't know exactly how this bias affect the extreme. So this is one problem. This is not a severe problem. This is a problem that will be solved in the near future, I guess. And there is another problem, which is the sampling problem. If this event has a return time of 1,000 years, say, it means that to study it in a model, you need to run the model maybe at least 10,000 years. And so usually you cannot do that. And so this is what I will call the sampling problem. And this is what I want to address today, how to study extremely rare events with a model. So when you have a rare event like that, if you assume that the dynamics is stationary, which is not quite true for climate, but let's assume that it is stationary to simplify the discussion, then you can plot, make a plot like this one. So on the x-axis, you have the time, and on the y-axis, you have the observable of interest. For instance, for us, the observable of interest will be the average temperature over Europe during 2 weeks or during a month. And so then you are looking at the extreme value. So in order to show the extreme value, I put a line here which is at 3.5 sigma, where sigma is just the variance, well, the standard deviation. And then I put dots when extreme events occur that goes above this threshold. And so this signal is just for a simple Ornstein-Uhlenbeck process. But you can do that for any process. And if the event is rare enough, then there are simple arguments that tells you that you should expect this red dot to be given by a Poisson statistics. The Poisson statistics means that the average time between two dots is given by an exponential law, like as you can see here on the plot on the right hand side. This is the waiting time, and this is the probability, and this is bins, and you see a fit with an exponential curve, and here the fit is extremely good. So this is for this simple toy model, but you expect this to be true for any dynamics for which the time you have to wait is much longer than the correlation time of the dynamics. Then if it is like that, the only thing that matters from the point of view of time is the average time. If you know the average time, you know that you will have a Poisson statistics with a rate which is given by just the inverse of the average time. Here lambda is the rate, and this is the average of the time. And so this is what is called the return time, this average time. Then if you want to apply this for problems for extremes, you would like to make a plot like this one, where in the first axis you have the return time, and on the other axis you have the amplitude of the event. So for instance, here the amplitude is a temperature anomaly during 90 days. So it's a seasonal temperature anomaly over France. And here you have a return time. Then you can read, if you are looking at an event with a return time of 1,000 years, then you see that the temperature anomaly is, for this model, it is a bit less than 2 degrees. So it's a bit like when you are looking at floods. And so you ask, what is the centennial flood? And you give an amplitude for the flood that will come back every 100 years. And so here you have the amplitude of an heat wave with a return time of 100 years, 1,000 years, 10,000 years, and so on. And so this is called a return time plot. This plot of a return time as a function of the amplitude, or the amplitude as a function of the return time. And it's basically what you need to, the curve you need to for risk assessment, risk analysis. So this is what you want to compute from your climate model. The problem is that if you want to go towards very long return time, it's very difficult to do because you need to run your model extremely long. And so this is the problem I want to address today. So this was the first kinds of events that matter because they have a huge impact. The second kinds of extreme events are abrupt climate change. So we know that abrupt climate change occurred in the past. So we know, for instance, the transition between glacial and interglacial. So those transitions are driven by external parameters. They are basically driven by the Milankovitch cycle and the change of the insolation of the planet. But there are other examples, for instance, what are called Dansgaard-Osger events, which are illustrated in these plots, which are not driven by external variation. They are just due to the internal dynamics of the climate system. And so here you see, for instance, the proxies of the temperature in the North Atlantic. So it's both coming from ice in Greenland and proxies in the ocean. And so you see that during the last 60,000 years, during the last glacial period, so you had abrupt changes of temperature. And so those abrupt changes of temperature appears very fast, something like they appear within a few years or a decade. And they are related to, we don't know exactly, there are several hypotheses. They are related to changes of the states of the ocean or ice discharge in the ocean. For instance, this is the case for the Heinrich events. So, well, we don't know exactly, but they are related to the coupled ocean, ice, atmosphere dynamics. And so here the question is a bit the same. I mean, what is the probability of these events to occur? So if we have a very good model of a coupled ocean, ice, and atmosphere, it costs a lot to run it. And so usually you don't have enough time to run it for tens of thousands or hundreds of thousands of years to see the extreme events that will be important. So those abrupt change occurred in the past on Earth, but they also occurred on Jupiter. So for instance, here you can see a picture of Jupiter jets. And something very drastic happened during the period 1939-1940. You see these bands here, they are related to jets, turbulent jets in the troposphere of Jupiter. And one of these jets disappeared during the period 1939-1940. And Phil Marcus called this Jupiter's abrupt climate change. And so it was just due to the turbulent dynamics of the troposphere of Jupiter, and suddenly it changed attractor. I mean, the global structure has changed. So for all this problem, the question is to compute the rare events and their probability. And so the scientific question is, what is the probability and the dynamics of those rare events? And the question I want to address today is how to sample those rare events, their probability and their dynamics. If you have a model and your model is complex, realistic, then usually it's extremely difficult. So usually you cannot just use direct numerical simulation. So the point would be to devise a new theoretical and numerical approach to try to compute this relevance. So today we'll speak mainly about the numerical approach. I will not speak much about the theory, but we work also a lot on the theoretical aspects. Okay, so let me begin with the extreme heat waves. So I will just begin by explaining basic things about extreme heat waves, something you can learn in a meteorology lecture, or so something that everybody knows in the climate or meteorology community. So it's the fact that an extreme heat wave is always coupled with an anticyclone anomaly. We always see, when we see weather at mid-latitude, we always see cyclone and anticyclone. And so we know that the cyclones are related to storms and bad weather in terms of rain and so on. And the opposite is true too. The anticyclones are related to good weather, and there is a feedback between anticyclone and heat. There is a feedback because when you have an anticyclone, the sky is clear, and then the heat of the sun heats much more the ground, and then you have much more evapotranspiration, and then you have a flux of heat, an important flux of heat from the ground, but you also have an important flux of heat from above because anticyclones are related to descending air. And so those two aspects are such that there is a strong connection between anticyclone and heat. And so here you can see maps. So you have two fields. So I will always show you these two fields. So you have, in colors, you have a temperature field. And the temperature field are below in colors. And above, you have the 500 hectopascal geopotential height field. So this is the height of the geopotential in the middle of the troposphere at 500 hectopascal. And so basically those lines are not the pressure lines, but they are closely related to the pressure lines, and the wind goes mainly along these lines. And so here what you can see is that because the lines are banded this way, here you have an anticyclone. And because you have an anticyclone, the wind is flowing this way. And so there is a strong connection here between the anticyclones, the pressure at 500 hectopascal, and the temperature. And so this is an average in a model simulation that has been done by Doll and collaborators in order to study heat waves that occurred over Russia. So let me show you a movie of what is called the jet stream. So what you see here is a movie from NASA, which comes from a weather model with data assimilation. And so you see the wind on the top of the troposphere at an altitude which is about 10 kilometers. So the colors show you the wind speed. And so you see that there is this band here of red colors, which shows that you have a jet, an area with a very strong wind that flows around the planet. And this jet is making meanders. So these meanders are directly related to the cyclones and anticyclone. Basically, when you have a meander like this one, you have an anticyclone here. So here you see that it flows all around the planet most of the times. So here you have a cyclone when inside the meanders on the top, you have an anticyclone inside the meander on the bottom. And so this is basically those are basically nonlinear Rossby waves, baroclinic waves, which are related to the transport of heat from the equator to the pole. And this is what makes mid-latitude weather. So what is an heat wave then, if you look at this dynamics? An heat wave will be when you have one such meander, like this one, that stop and remains blocked in the reference frame of the planet. Here I have stopped artificially the movie, but sometimes it happens that actually there is a block state in the sense that the jet, the wave speeds of the waves on these jets will become zero, and it will become blocked in the reference frame of the planet. Then for a very long time you have an anticyclone, and then the heat can grow and increase a lot. So this will produce an heat wave. So if you want to study heat waves, you basically have to run a model that have this dynamics, and to study this blocking period, or this period for which you have an extremely long heat over an area. So this is what we will do in this talk. So a key question is about the anthropogenic causes of heat waves. So this is, for instance, what you can find in the last IPCC report. This is work that has been done by Otto and collaborator after the Russian heat waves of 2010. And so what they have done, which is very good, is to make a plot like this one. So it is a return time plot, as the one I presented at the beginning. So here you have the return time, and here you have the amplitude of the heat waves. So in this case, they have chosen to compute monthly average temperature over Russia. And so you see that 19 is the average value. It is the value that you will see every year. But if you look at 100 years return heat waves, the heat waves that has a return time of 100 years, if you look at the green curve, you see that it has an amplitude of 25 degrees. And it is more or less what happened this summer in 2010 in Russia. So if you want to address the anthropogenic causes of the heat waves, what you want to do is to compare two different climates. So that's why you have two curves here. One curve is for the climate during the period 1960-1969. So basically to running a climate model with the carbon dioxide value of these decades, and with the sea surface temperature of this decade. And the blue curves is the curves for the decades of 2000-2009. And so then comparing the two curves, we can see how the probability of the heat waves has changed. And so you can see that basically the heat waves, you see that heat waves with 25 degrees during a month in the new climate has a return time of only 30 years. So it is 3 times more frequent. It will come back 3 times more often. And so this way you can say, you can assess that climate change has a big impact on the probability of these extreme events. So this is good. This is a good way to see these events probabilistically. So the point is, can you trust this curve? I mean, in order to make such a curve, you need a model. So the problem is, can you trust the model statistics for those curves? And so one point is, as I was telling before, is the sampling problem. If you want to make a curve like this, if you want to trust this point with a 100 years return time, if you want, for instance, to have 100 events, you need to make a simulation which lasts at least 10,000 years. So usually you are not able to do that with the best model. So what we want to do here is how to study a 10,000 year heat waves with a simulation that costs, for instance, only 200 years. So basically what we want to do is to make a computation for which we are able to compute and to simulate the extreme events, but not to compute the very long time for which nothing interesting happens from the point of view of the extreme events. And so this is what we will address today, how to sample rare events in an efficient way. So we have first done this a demonstration of our method using a model which is called the planetary simulator, PLASIM. It has been developed at the University of Hamburg. So it is a simple GCM with a coupled atmosphere, sea ice, vegetation, ocean, and soil. It has a resolution which is more or less the same as the one of the best model. It is a bit lower in terms of resolution, but the physics in this model is rather simplified, such that it runs much faster. And so it runs typically 100 times faster than the model that are used in order to make the CMIP experiment for the GIEC, for the IPCC report. And so, but recently we have also demonstrated the use of rare event algorithm with IPCC, with the models that are used for the IPCC report. So even if most of what I present today is with the PLASIM model, I mean, we have done the same with more complex models. So this is how the dynamics look like in this model. So here you can see, you will always see the two same fields. So here the color are the temperature anomalies. It's the temperature minus the average for the model. And so the lines show you the 500 hectopascal geopotential height anomaly. So what you see here with these lines is basically the jet stream, the same jet stream that I have shown you before on a global movie. And so you can, when the meanders of the jet stream are related to cyclone and anticyclones. And so you see here there is an anticyclone, and it is hot when there is an anticyclone. So those models are the ones that are typically used for climate experiments, but they are not as good as the weather model. They are a bit more sluggish, they are a bit less turbulent, but still they are very interesting tools. Now I will be interested in heat waves. So I will compute average surface temperature. So I take the temperature, the surface temperature in the model, and I will average it over Europe. So Europe is this red area here in this map. So this is a spatial average, but I also do a time average. I am making a time average here during a time capital T, where capital T will be 1 week or 2 weeks or a month or 90 days. I will change the value of time. So I don't see if anybody asks me some question, but please stop me to ask me question. So this is a time series of this time average temperature for the model. So here you see we run the model 1000 years, and you can see the time series. So you have two curves. The light blue curves is just the 6-hour temperature time series, and the dark blue curve is the temperature average during 45 days in this case. And so this dot here and triangle show you an example of an heat waves. So here we zoom in the heat waves. And so you see that now it lasts, the time is in days. And so you see that this is the extreme value for the temperature. So here we have an heat wave with 2 degrees in excess of the typical temperature during 45 days. And you see that the heat waves last about 100 days. And so the question is, what is the probability of these events, and can we simulate many of these events with this model? So in order to do that, we will use an algorithm that was developed in statistical physics and that we have used for many other applications before. And so this is called a rare event algorithm. So here it's a rare event algorithm which is based on the large deviation theory. So that's why we were calling it a large deviation algorithm. So as you have already understood, the problem is that the event is too rare. And so for instance, here, I just assume on this slide that I will compute the probability of the event. So the probability of the event here is just, so let me show you this plot first. So here we want to look at the probability to be in the red area here for this blue PDF, probability distribution function. So this is our rare event. So the problem is that it is rare. So if you compute the probability to be in this red part, this is what I do here with this formula. I just average the PDF with the indicatrix that I have in the set A, and this is this average, and this is the number I want to estimate. So I can estimate it naively. This is what we always do. I just count the numbers of events that occur when I pick a random sample of this distribution. So for instance, I could do that running a model extremely long, and then n is something like the numbers, the time of the model divided by the correlation time of the model. And if I do that, the problem is that if I compute the variance, and if I compute the relative error, then I find that the relative error is 1 divided by the square root of gamma A multiplied by n. So it means that I need n to be large for the relative error to be small. But the problem is that there is this gamma A in front of n here, and gamma A is very small. So it means that I need n to be extremely large. So it is obvious in a sense. It means that if you want to have a relative error of 1%, you need to have to see your events at least 10,000 times. Or if you want a relative error of 10%, you need to have to see your events at least 100 times. So this is the problem. So in statistics, there is a way to deal with this problem, which is called importance sampling. So let me assume that rather than picking samples with the blue PDF, I would be able to pick sample with the green PDF. Then it would be perfect because my red events becomes a common one. It becomes typical. Then it will be very easy to estimate the probability. So if moreover I know the mathematical relation between the two, I know that rho is L multiplied by rho tilde, then I can use this relation to invert the computation. So I can compute gamma A for the blue PDF using the estimation from the green PDF, here rho tilde, and multiplying by this function L that I know. And then I estimate gamma tilde A, and my estimation is very good because the event is now common. So I am able to estimate this small value with an estimator that uses a common samples of some distribution. So this sounds good, but how can I do that with a model? It sounds like magic. The model, how will you be able to do that? And so this is where we will use this rare event algorithm. So we will use an algorithm that will make exactly what I described before. P naught here will be my model statistics. The statistics I would get with the model without doing anything. It is just like the blue PDF here. P tilde will be the green PDF. It is what my algorithm will give me. And so the relation between the two will be a multiplication by this exponential factor. And this exponential factor, I will choose it to be the exponential of k multiplied by the time average of the surface temperature over Europe. A here will be the surface temperature over Europe. K is a number that I will pick. It's a number of algorithm. So if k is positive, it means that I will shift a lot the distribution towards the positive value of the time average temperature over Europe. So I will do exactly the same as the green PDF here. So then I will just have to tune the value of k in order to make my rare events typical. And so here this number here in the formula is just a normalization factor such that both P naught and P tilde k are both a distribution function. So how to do this in practice? So in order to do that, I will run ensemble simulation. I will run hundreds of simulation in parallel. So here the number of simulation is capital N. Xn is the trajectory of one of the simulation. I will stop my simulation each time tau. Tau will be the correlation time of the model. So for instance, for a climate model, the correlation time is just like for weather. It's about, it's a few days, it's about a week. So I will stop here every 5 days. I will compute this weight here. So you see this, this weight, this exponential is just the same as here, except that I take just the increment for this time integral. So I take this time integral increment between time tau. So this gives me a number, which is the number that comes in this probability here. Those are weight, such that those numbers are weighted in order to give a probability 1. And so those weight, I compute it just by normalization. And so this basically gives me a number which is the probability of each of these trajectory that I should have in order for this formula to be correct. And so then, based on this number, I will delete some trajectory or clone them. So the one that have large value here, I will clone them. So for instance, if I have a number here which is 2.5, I will clone my trajectory 2 or 3 times such that on average it is 2.5. And if this number is lower than 1, then I will cancel my trajectory. And so then with this algorithm, I will be able to actually make this formula correct for this ensemble simulation. So this is how it looks like in practice. So this is time. This is my observable. So initially I have n ensemble of my model with the typical value. I will stop. Some trajectory will be cancelled. They will be cloned on the other trajectory based on this selection mechanism. And so I do that a lot of time. And so after some times, I have an ensemble which statistics has been biased by comparison with the normal statistics. So I have a biased ensemble for my model, but the point is that I know exactly how it has been biased. It has been biased according to this formula. So then I am able to invert the formula and to compute the probability for the model.
Freddy?
Yes?
Yeah,
Yes?
there are two questions.
Yes?
One from Balaji.
Yes?
Regarding tau parameter, and what if tau is much larger than a few days? And Balaji was referring to ocean low frequency variability. Maybe Balaji, you can complement.
Yes. Yes, please do, Balaji, if you want.
Yeah,
or I can answer just this.
If you can hear me.
Yes.
So yes, so you mentioned that the tau decorrelation time was on the order of few days.
Yes.
But in a coupled climate model with low frequency variability, you do have modes that are much longer than a few days. So there is going much beyond the Lorentz time. There is coupled, like ENSO, for example, gives you much longer correlation times.
Yes. So, here we have not, I mean, in the model we use, sorry. Yes, here the model we use does not have this low frequency variability. So there is just one correlation time, which is the mid-latitude weather correlation time. And so if we would have much longer time, so then we would have to basically to independently study situation for different value of this long correlation time. So for instance, this is something we are doing now. So what we do is we condition our simulation on the states of the ocean. And then we obtain results which are conditioned on the states of the ocean. And then we can reconstruct everything and see the probability condition on the state of the ocean. So we do have to do something specific in order to take into account the fact that there are more than one important time scale. So we run the algorithm to have rare events for the mid-latitude weather condition on other time scale.
Okay, thanks, Freddie. I look forward to seeing your new results also sometimes.
Yes, but this is, yes, there are many questions like that. I mean, we are making progress slowly. So we have begun with a model which is very simple. And actually, the first experiments, we didn't add a seasonal cycle. And now we can do that with the CSM model with seasonal cycle. But we still don't have this low frequency variability. But this is something we are working on now.
Okay, and Freddie?
Thank you.
Yes?
Thanks. There was a second question regarding the cloning of the trajectories.
Yes.
Which was, how do you clone? What do you mean by cloning trajectories, probably?
Yes, so here we make a new trajectory with the same initial condition as the other one, and we put a small perturbation in this initial condition. And then, because the dynamic is chaotic, the two trajectories separate on a time scale of order of tau, actually, the correlation time. So we just perturb a bit and so we make sure that this perturbation is small enough such that it does not affect the statistics.
Thanks. I think it was clear.
So there are many questions I don't, there are many details I don't explain. Sorry, I cannot do that because it would be very long, but those are very important questions. I understand. So this is just to show the result. So here you see the PDF of the model in black, which is what we call the control run, and the PDF we get for the rare event algorithm for the time average temperature in red. And so you see that here with this numerical computation, we made the heat waves with 2 degrees anomalies during 90 days, typical. And then you can see on the right-hand side the numbers of heat waves we obtain as a function of K. K, I remember you, is the parameters of the algorithm. The stronger K, the stronger the bias in the algorithm. So here for K equals 0, we just have the model. And so we had 8 heat waves in 1,000 years. And here with K equals 50, we obtain several hundred heat waves with a simulation that was lasting actually 200 years. So we obtain several hundreds more heat waves using this algorithm than in the control run. And so this is basically the way we have made the plot of this return time for heat waves in our paper published in PNAS a few years ago. So here the black curves come from the control run. We just run the algorithm. We just run the model without algorithm. And the black curves comes using the algorithm. And the cost for the red curve is the same as the cost for the black curve. And so with a total cost of 1,000 years, we can estimate return times of order, for this case, of 10 to the 7 years. And so this is for heat waves which have a time average of 90 days. So the results are a bit less striking, but still very interesting when we average only during 2 weeks or 1 month. So I will skip many things just to show you that we have also studied the dynamics. And so this is the conditional statistics on the heat waves, what are called teleconnection patterns in the climate community. And so this is not a teleconnection pattern for a typical fluctuation, but it is a teleconnection pattern for an extreme heat wave. So usually you cannot do that because you don't have enough data. So here we were able to do it, and it is statistically significant because we have a lot of data. And so you can see here always the two same fields. So look at just the temperature, for instance. So the temperature are the colors, and you see that there is a wave number 3.
Yeah. And maybe, yeah, there was an additional question from Angélique again. Angélique, would you like to ask your question?
Yes. Hello, Freddie. I was wondering, when you are showing those curves of the return time function, it seems pretty well defined. So I was wondering, when you are doing this, not emulation, but when you are reproducing many more rare events with your methodology, can you compare how well it compares the return time function with just a simple extrapolation of the return time function that you have for well-defined events that you have reproduced enough time? So in simpler terms, can we just extrapolate what is the error that we would do if we just extrapolate the return time function towards even rarer events?
Yes, so yes, we have not done that because we don't just, I mean, many people do that. So for instance, you can use extreme value statistics to extrapolate, right? So we have not done that. I mean, we don't know exactly, but we will do that. I mean, we began to discuss this a bit with Philippe Navo. But the point is that we don't just want to extrapolate. We want to understand the dynamics. So we really want to look at what's happening, whether the dynamics is well reproduced in the model, and then to make the physics and the dynamics of the model to see whether the processes are the ones that are correctly computed by the model. So it's not just about plotting this curve.
Okay, thank you.
But the question is important. The question you ask is important, and we will do that soon. So yes, I was showing you this teleconnection patterns. The teleconnection patterns here that we got for heat waves over Europe. So this is the map of the July 2018 heat waves that has been observed. This is the observation in reanalysis. So it was 6 months after we published this work. And so you see that by chance, we got exactly a Scandinavian heat waves in 2018, just like the one we are describing here. And you see that the pattern is very similar. You see it is correlated with heat waves in Canada and in Korea and Japan, and anti-correlated with cold over Greenland and over Russia. So just like the one we were describing before. So this is just by chance, but just to say that a simple model like PLASIM has a mid-latitude dynamics, which makes sense actually. Okay, so recently we have done the same with the CESM model, and so this is the plot that shows you that the relevant algorithm work well with CSM model. CSM model is a model from NCAR, which is one of the models which is used to make the CNIP experiments and many other experiments for the IPCC. So with this new plot, we show that we can do that with the top class climate models and with a seasonal cycle. So I am late. So can I have 5 more minutes, Ronan?
Sure. Even more. I mean, yeah.
So yes. So the basic conclusion for extreme heat waves is that this large deviation algorithm, they provide a wonderful tools to sample relevance. And there are still a lot to do at a methodological level. We are progressing, but we think that they should be useful in the future to study extreme events. So now there is a point is that we know how to make this this relevant algorithm working for extreme heat waves, but we are not yet confident that they will work for other extremes. So for instance, if we would like to study extreme storms with this algorithm, we don't believe that it will work. The point is that the dynamics to get extreme storm is much more intricate and much more difficult. An extreme heat wave is just something which is persistent. So in a sense, from the point of view of dynamics, it's very easy. You just have to select persistent events. For extreme storm, it's much more difficult. And so we have to make some progress. And for this, I will explain you how we want to couple machine learning with relevant algorithm in order to be able to go towards studying other kinds of events. And here, does it work? So you see now it has the slide has been changed. You see this plot here with A and B, right?
Yeah, right.
So A, let's think of A as a typical state of my model and B as an extreme heat waves. So I run ensemble of simulation. Here I have just 3 for the sketch, 3 simulation. I look at how extreme I get, and then I will cancel the one which is less extreme and replace it by a new one, which is the purple one here, for which I use the initial condition of the blue one, of the number 2 here, which is on the same level line as the for this function Q. So the function Q here is a function that helps me to measure how far I want in the direction of the extreme. And so this is called the score function or a selection function. So this is the function that I use in this algorithm to select the good trajectory. So in all of this algorithm, I always have a score function or selection function. So if my selection function is good, then my algorithm will be wonderful. And so in the case of heat waves before, the selection function was just that the time average temperature was large and it was good enough. But for other extremes, I will need a better score function. And so I will need to learn it. And so the key idea here is that the optimal score function for a ray event algorithm is called the committor function. So I don't tell you more, but the point is that what I want to do is to learn the committor function from data. So I want to do a feedback control loop. So I have data that comes from direct sampling. It gives me some data. For instance, I already run my model a few centuries or something like that. I will use a machine learning approach to learn the optimal score function, the one that actually describe well the dynamics that lead to the extreme events. And then I will use this score function for my ray event algorithm. This will give me much more data with the extreme. And then I will be able to make better my learning. And I will loop. This is what I call a feedback control loop. So I will run several times my machine learning, my ray event algorithm, such that they will work together. The problem of machine learning for extreme is that you don't have enough data. It's good, but it doesn't work very well because you lack data for the extreme. The good points of ray event algorithm is that it will give you much more data. The problem of a ray event algorithm is that you need a good score function. And so for it, you need machine learning. And so the advantage of ray event algorithm is exactly the drawback of machine learning and vice versa. So that's why we want to couple the two approaches together. So what we have done is to use a classical convolutional neural network in order to learn the probability to have an heat wave, which is basically the committor function in this case, the optimal score function. And so this is a work we do with people in my lab, Patrice Abry and Pierre Borgna, which are colleagues from traitement du signal community in my lab. And Valérian Jacques Dumas, Valérian is a master student that has done the machine learning work. So here the question was using 500 hectopascal geopotential height or using surface temperature fields or using both with these classical convolutional neural networks, can we learn the probability to see an extreme heat wave? So we have done that. I mean, this is there are a few groups that do that for extreme events around the world. So what we do here is a convolutional approach for machine learning. So this is just to illustrate how the loss function evolved during the learning process. So here there are three cases, one with surface temperature only, one with geopotential height only, and one with both.
Yeah, and I may have a question regarding the way you apply machine learning and the CNN. Oh, probably you were in the next one because you presented the CNN.
Okay. Yes.
Here I have a question. Yeah, you were even in the next one. Okay.
Yes.
You were frozen there. My question is, in the CNN, the input you provide is the temperature and geopotential maps at the same date and or before, I assume, the extreme event.
Yes. So far it's the extreme events. It is an event that lasts 2 weeks in this case. it is an extreme for the time average temperature during 2 weeks.
Okay.
Then we use the field at the beginning, at the first
Date.
day, at the first day of these 2 weeks.
Okay.
So it's a prediction for the next 15 days, let's say.
For
So
the same zone area or for the entire domain?
Yes, we are looking at the field today, and we predict the probability that during the next 15 days, you will have heat, which is extreme.
Okay.
And so we could also have a lag, which is different. Here, the lag is 0 in what I just explained you. So we could have a lag, tau, which is not 0, which is 1 week before or 2 weeks before. But we have not done that yet, but this is obviously what we want to do. We want to try to see the predictability ahead of time and to see how far we can go ahead of time.
Okay, thanks.
So this is just the result. Here, I will not explain the detail of this table, but just look at what is in the blue part here. You see the average Matthew correlation coefficient for this prediction. And here you can see that you have 3 columns, one for heat waves with which 5% return time, heat wave with 2.5% return, and heat waves with 1.25% return. And so for this 3 prediction, you see how good it is. So if it would be perfect, it would be 1. If it would be nothing, it would be 0. And so you can compare then the value for what happens if we use only the 500 hectopascal geopotential height, or if we use both fields, the 500 hectopascal geopotential height and the temperature field. And so you see that here it's better with the temperature field, with the combined fields. And so you see that the prediction is interesting. It's not very good, but it's interesting. We have a Matthew correlation coefficient, which is about a third. And so this is the key point is that with this conventional approach of machine learning for the probability of extreme heat waves, with this convolutional neural networks, it gives very interesting results. But the results are not amazing. So here, even with a learning data set of 1,000 years, and with a lag time tau equals 0, it's not exceptional. And so this is clearly, this is very interesting, but this is clearly insufficient to be relevant for most applications. And so this is why we want to, I think this is a common problem in climate that our machine learning approach, like many others, suffers from a problem of a lack of data. And so this is exactly why we want to couple this machine learning approach with a relevant algorithm this way in order to solve this lack of data problem. Basically, we don't have enough relevance, but we learn something which is interesting. And so we want to use this interesting information with a relevant algorithm to do better next time. So I will stop here. I am sorry for the delay and for the interruption.